There is a place in our galaxy where the night sky never goes dark. Not because of city lights or a moon that refuses to set, but because the stars are so dense, so relentlessly packed together, that darkness simply has nowhere to stand. And those stars are not drifting gently the way ours does across the slow turning of the galaxy. They are moving fast. So fast that a solar system, an entire solar system, with its planets and moons and long elliptical orbits, would cross our sky in days, not years, not centuries, days. Now, imagine standing in that sky, and then imagine what lies at its centre. Something with a mass of 4 million suns compressed into a space smaller than the distance from here to Saturn. Something that bends the fabric of space-time so severely that the stars nearest to it orbit not in the leisurely years it takes our Earth to circle our Sun, but in decades, moving at thousands of kilometres per second just to avoid falling in. Something that, on its quieter days, is content to simply sit there, patient and enormous, like a very massive, very patient thing that has learned that patience is easier when you have the gravity of 4 million suns on your side. This is the centre of the Milky Way, and tonight we're going there. Hello, and welcome to the Sleepy Astronomer. Tonight we're going to visit the most dangerous place the universe has ever produced. Not the most dramatically lethal, not the most instantly fatal, but the most comprehensively, inescapably structurally hostile environment that physics is capable of building at scale. We'll travel from the comfortable darkness of our own neighbourhood through the crowded, radiation-soaked heart of the galaxy, and we'll meet the sleeping giant at its centre. We'll ask what happens when that giant wakes, and we'll discover quietly that the fact you are alive to listen to this is not entirely unrelated to the fact that it hasn't. If you're settling in for the first time, welcome to these gentle explorations of cosmic mysteries. And if you've drifted with me before through deep time and distant stars, it's wonderful to have you back for another journey. If these peaceful wanderings through space and time bring you comfort or curiosity, don't forget to follow and subscribe so you don't miss the next journey into the cosmos. And if tonight's destination intrigues you, the most dangerous address in the universe, hiding in plain sight behind a smudge of the Milky Way, a gentle rating and share helps others find their way to these nocturnal wanderings about the cosmos. For those whose curiosity turns downward rather than up, to the slow grind of tectonic plates, the patience of rivers, the deep biography of the Earth itself, the sleepy geographer is waiting. And for those drawn to darker, quieter mysteries, the sleepy investigator has something for you as well. Here's what makes this story so strange. The most dangerous place in the universe is ours. Not in the sense that we own it, we very much do not, and any attempt to visit would go poorly in ways that are difficult to overstate, but in the sense that it sits at the centre of our own galaxy, 26,000 light-years away, invisible to the naked eye behind curtains of dust and gas, quietly going about its business while we sleep. We are not talking about somewhere exotic and distant, some far-flung quasar blazing at the edge of the observable universe. We are talking about home, the Milky Way, the smear of light that ancient humans watched from hillsides and tried to make sense of with the tools available to them, which were considerably more poetic than precise. That smear contains, at its heart, an environment so extreme that the ordinary rules of matter begin to buckle and rearrange themselves around it. And yet the universe, in its vast indifference, has placed us at a comfortable remove, far enough that the radiation cannot reach us, far enough that the gravity is imperceptible, far enough that we can study it, name it, image it and marvel at it from the warmth of wherever we happen to be lying right now. So, take a deep breath, let the quiet settle around you, and find your most comfortable position. Tonight we're going to the most dangerous place in the universe, and we're going to arrive home completely unharmed, which, all things considered, is the best possible outcome. Before we get to the most dangerous place in the universe, it is worth pausing to appreciate how many places are merely very dangerous. The universe is not, on the whole, a welcoming environment. It was not designed with guests in mind. If you were to step, unprotected, into the average patch of space, not a particularly exotic patch, just the ordinary void between planets, you would have approximately 90 seconds before the situation became irreversible. The vacuum would cause your blood to begin boiling at body temperature. The cold, if it could be called that, would not so much freeze you as simply carry your warmth away with quiet efficiency. The radiation, depending on your proximity to the nearest star, would begin doing things to your DNA that your body's repair mechanisms were never designed to handle. Space, in other words, is not hostile in the way that a storm is hostile, or a desert, or a mountain in winter. Those things are difficult, space is categorical, and yet, within that general hostility, there's a great deal of variation. The universe operates in matters of danger along something like a sliding scale, a long spectrum that runs from unpleasant but survivable at one end to not worth thinking about at the other, with a great deal of interesting territory in between. Consider for a moment the radiation belts that wrap around our own planet. These are regions of space, beginning a few hundred kilometers above Earth's surface, where charged particles from the Sun become trapped by our planet's magnetic field and accumulate into invisible bands of radiation encircling the globe. They were discovered in 1958 by the physicist James Van Allen, who attached a Geiger counter to one of the first American satellites and found, to his considerable surprise, that the counter went silent, not because there was no radiation, but because there was so much of it that the instrument was overwhelmed. The Van Allen belts are not lethal in the way that a gamma-ray burst is lethal, but they are not somewhere you would want to spend your afternoons. Astronauts pass through them as quickly as possible, and spacecraft are carefully shielded to manage the exposure. They are a hazard, a manageable one. Move further out, and the dangers shift in character. The surface of Venus, for example, presents a different set of problems entirely. The atmosphere is 90 times denser than Earth's, which means the pressure at the surface is roughly equivalent to being 900 meters underwater. The temperature is around 465 degrees Celsius, which is hot enough to melt lead, and this is true both on the day side and the night side, which tells you something about how efficiently the thick atmosphere distributes heat. The atmosphere itself is composed largely of carbon dioxide, with clouds made not of water droplets, but of sulfuric acid. The few spacecraft that have managed to land on Venus have survived for approximately 2 hours before the environment finished them off, which, under the circumstances, seems like a reasonable effort. Venus is not somewhere you could visit, but it is somewhere you could theoretically approach and describe and understand. The further you move from the ordinary, from planets and moons and the comfortable middle distances of a solar system, the more the scale of danger begins to change. It is not just that things become more lethal. It is that the radius of lethality expands. A storm on Earth is dangerous within its own boundaries. An exploding star is dangerous across a considerably larger area. Neutron stars offer a useful illustration of this expansion, A neutron star is what remains when a massive star exhausts its nuclear fuel and collapses, not into a black hole, which requires even more mass, but into something almost as strange. The collapse is so complete and the resulting pressure so extreme that individual atoms can no longer maintain their structure. Electrons are forced into protons, producing neutrons, and the entire object, which may have started as a star several times the mass of our Sun, compresses down to a sphere roughly 20 kilometers across. 20 kilometers, the width of a modest city, and it contains more mass than the Sun. The consequences of this compression are difficult to hold in the mind comfortably. At the surface of a neutron star, gravity is approximately 200 billion times stronger than what you experience lying where you are now. If you could somehow place a marshmallow, a standard-sized one for the sake of argument, onto the surface of a neutron star, the gravitational force would compress it in the first millisecond to something thinner than an atom, releasing in that compression more energy than a nuclear weapon. This is, admittedly, an unusual fate for a marshmallow, but it illustrates the point. The region of space around a neutron star that could be considered safe, in the loose sense of not immediately and overwhelmingly lethal, extends for a considerable distance. The intense magnetic fields, the radiation pouring from the poles, the gravitational effects on anything that comes too close, all of these create a zone of hazard that stretches well beyond the object itself. Approach within a few hundred kilometers, and tidal forces, the difference in gravitational pull between the near side of your body and the far side, would begin to stretch you in directions that your body was not intended to travel. Approach closer still, and the radiation alone would be sufficient to end the discussion. But here is the important thing about neutron stars. For the purposes of where we're going tonight, they are points, extraordinarily dangerous points, surrounded by extraordinarily dangerous fields, but points nonetheless. Their influence, however severe, is local. It falls away with distance, as all gravitational and electromagnetic effects do, following the familiar mathematics of the inverse square law. The further you travel from a neutron star, the safer you become, and the rate at which safety improves is, relatively speaking, generous. This is what changes as we move up the scale. Not just the intensity of the danger, but the geometry of it. Some environments are dangerous at a point, others are dangerous across a region, and the most extreme environments the universe produces are dangerous across regions so vast that distance begins to lose its reassuring quality. You cannot simply move away from them. There is no nearby patch of calm to retreat to. The hazard is not a feature of the location so much as the entire surrounding territory. There is a useful way to think about this, which physicists sometimes call the lethal radius, the distance from an object or event at which the energy or radiation or gravitational disruption it produces becomes sufficient to be fatal. For a neutron star, this radius is measurable in hundreds of kilometers, or at most a few thousand, depending on the mechanism. For a supernova, the explosion of a massive star at the end of its life, the lethal radius expands dramatically. A supernova within 30 light-years of Earth would be sufficient to cause serious damage to the ozone layer, exposing the surface to levels of ultraviolet radiation that would be deeply unpleasant for anything that had evolved to live under a protective atmosphere. Within about 10 light-years, the effects become catastrophic. Within a light-year, they become essentially complete. And a supernova is, by cosmic standards, a fairly routine event. Stars explode all the time. Our galaxy produces roughly 1 or 2 per century, which sounds infrequent until you consider that a century is not very long and a galaxy is very large. They are the universe's way of recycling, distributing the heavy elements forged in stellar cores back into the interstellar medium, where they will eventually find their way into new stars, new planets, and, in at least one documented case, creatures capable of worrying about the whole process. Supernovae are dramatic. They are lethal across significant distances, but they are events, brief, localized, and finite. They happen, they expand, and they fade. What we are interested in tonight is something different. Not an event, but a place. Not a moment of violence, but a sustained condition. An environment that does not explode and disperse and leave things quieter than before, but simply continues, day after day, century after century, being exactly what it is. The most dangerous place in the universe is not the most dramatic. It is not a single explosion or a single object or a single overwhelming force. It is a region where multiple extreme forces overlap and reinforce each other, creating conditions that are not catastrophic in the brief, spectacular way of a supernova, but comprehensive in a quieter and more thorough way. Radiation from dozens of sources, gravity on a scale that warps the paths of light, tidal forces that make a neutron star's gravitational gradient seem gentle, and at the center of it all, patient and enormous, something that has been sitting there for longer than the Earth has existed, and will continue sitting there long after the sun goes out. We are making our way toward it, but it is worth taking the journey slowly. The universe, as we have established, is not in a hurry. Neither are we. We live as galaxies go in a quiet part of town. Our solar system sits roughly 26,000 light-years from the center of the Milky Way, tucked into one of the galaxy's spiral arms in a neighborhood that is, by the standards of the cosmos, fairly unremarkable. The stars around us are spread at comfortable distances from one another. The nearest, Proxima Centauri, is about 4 light-years away, which is close enough to be called a neighbor, and far enough that you would never accidentally borrow its parking space. The interstellar medium, the thin soup of gas and dust that drifts between stars, is sparse. The radiation environment, while not something you would want to stand in without protection, is gentle enough that a planet with a decent magnetic field and a serviceable atmosphere can get on perfectly well. Life, as we are aware, has managed to not only exist here, but to become sufficiently comfortable that it has started building radio telescopes and asking questions about the rest of the galaxy. The rest of the galaxy, it should be said, is considerably less relaxing. The Milky Way is a barred spiral galaxy, which means that if you could somehow rise above it and look down, a perspective no human has ever had, and is unlikely to have for some time, given the distances involved, you would see a flattened disk of stars arranged in sweeping arms that curl outward from a dense, luminous center. That center is what concerns us tonight. It is not just brighter than the surrounding galaxy. It is different in kind. The conditions there belong to a different order of existence entirely, and the journey from where we are to where we are going is, in a sense, a journey between worlds. To travel from our neighborhood toward the galactic center is to watch the universe become progressively more crowded. In our region of the Milky Way, stars are separated by distances measured in light-years, vast, empty stretches of space between one stellar system and the next. As you move inward, those separations begin to shrink. Slowly at first, then more noticeably, the stellar density increases. The background glow of the galaxy, which from Earth appears as a pale smear across the night sky, would resolve, if you were moving toward it, into something richer and more complex. More stars, more light, more of everything. By the time you reach the inner galaxy, the region sometimes called the central molecular zone, a ring of dense gas and dust that encircles the innermost few hundred light-years of the Milky Way. The environment has changed substantially. This is not the comfortable suburb we left behind. The central molecular zone is a turbulent, compressed, chemically strange region where giant molecular clouds drift through space in a state of slow, perpetual agitation. These clouds are vast, some of them containing enough material to form millions of stars, and they are being stirred and shredded and reshuffled by the gravitational forces emanating from the center. Stars form here at a higher rate than in the outer galaxy, but they also die here faster, and the remains of their deaths, the remnants of supernovae, the expanding shells of ejected gas, accumulate in the interstellar medium, making the whole region hotter, more ionized, and more energetically chaotic than anything you would find in our quiet corner of the spiral arm. The radiation environment in the central molecular zone is worth pausing on because it sets the scene for what comes next. In our neighborhood, the interstellar radiation field is gentle enough that it barely registers as a consideration. In the inner galaxy, it is not. Massive stars, young, hot, intensely luminous, form in clusters near the galactic center and pour ultraviolet radiation into the surrounding gas with a profligacy that would seem excessive even by stellar standards. The gas glows in response, lit from within by the energy of the stars embedded in it, and the whole region shimmers with a light that has nothing to do with the quiet, steady radiance of a mature star like our Sun. It is a younger, more restless kind of brightness, the kind that suggests the environment has not yet decided what it wants to be. And then there is the question of what you would see if you were somehow standing in this region and looking up. On Earth, on a clear night far from city lights, you might see a few thousand stars with the naked eye. It is a sight that has moved human beings to poetry and religion and navigation, and eventually to building the kind of instruments that can count the stars more precisely than poetry requires. It is, by any reasonable measure, a beautiful sky. But it is also, by the standards of the galactic center, a sparse one. The stars you see are spread across enormous distances, each one a distant point of light separated from its neighbors by years of travel at the speed of light. In the inner galaxy, that changes. The stellar density near the galactic center is roughly 1 million times higher than in our neighborhood. Not 1 million stars where we have one, that would be dramatic enough, but stars packed so closely together that the distances between them shrink from light years to fractions of a light year. The night sky from a planet near the galactic center, if such a planet existed and if anything on it had eyes, would bear no resemblance to the sky we know. There would be no darkness between the stars. There would be no patches of black where the eye could rest. The sky would be filled in every direction with a dense, overlapping blaze of stellar light, each star close enough that it would appear not as a point but as a resolved disk, a visible sphere of fire rather than a mere suggestion of one. It would never be night, not truly. The combined light of the surrounding stars would be sufficient to read by, to cast shadows to warm the surfaces of whatever lay beneath it. The concept of darkness, the cool, quiet absence of light that we associate with rest and sleep and the particular comfort of a sky full of distant, unthreatening stars, would simply not exist there. The universe, in this neighborhood, keeps the lights on permanently. This is already a profoundly different environment from our own, and we have not yet arrived at the center. The galactic center proper, the innermost few light years of the Milky Way, is a place that even the most well-traveled astronomer has only ever seen through instruments, because it is hidden, not by distance alone, though 26,000 light-years is a perfectly adequate hiding place. It is hidden by the sheer density of the material between us and it. Dust and gas absorb visible light with such thoroughness that the galactic center is entirely invisible to the naked eye and to ordinary optical telescopes. If you point a standard telescope at the heart of the Milky Way, you see nothing of consequence. The curtain is too thick. It was not until the development of infrared and radio astronomy in the 20th century that astronomers began to see through that curtain, and what they found surprised them. The galactic center was not a quiet hub, around which the rest of the galaxy turned in stately order. It was active, crowded, home to star clusters so dense they had no equivalent elsewhere in the galaxy, home to gas clouds moving at velocities that made no sense unless something of enormous mass was pulling them. Home, it eventually became clear, to something sitting at the very center of everything, something compact, invisible, and extraordinarily heavy. We're close now, close enough that the ordinary metaphors for cosmic distance, the light years, the vastness, the emptiness between things, begin to give way to something more concentrated. The universe has been expanding around us for 26,000 light years, and now it is about to do the opposite. It is about to compress. And at the point of maximum compression, something waits that we have been circling, in one sense or another, for the entire journey. It is time to look at what is actually there. Imagine you are floating in space, very still, at the edge of the innermost region of the Milky Way. Not falling toward anything, not moving in any particular direction, simply suspended, the way you might imagine drifting in warm water on a calm evening, except that the water is vacuum and the evening is a sky that blazes in every direction with the light of 1,000,000 packed stars. Beneath you, if beneath is even a meaningful concept where there is no ground to orient yourself against, the galaxy spirals away in both directions, its arms curling outward into distances you could not meaningfully imagine even if you tried. And ahead of you, at the point where the stellar density is highest, where the light is brightest and the gas clouds most agitated, and the orbits of the nearest stars most violently curved, there is something you cannot see. Not because it is small, it is not small, but because it is dark, and because darkness in a place this luminous is itself a kind of presence. What sits at the centre of the Milky Way is called Sagittarius A star. The name is not particularly romantic, but astronomers tend to prioritise precision over poetry, which is perhaps why they are better at finding things than naming them. It is a supermassive black hole, a term that has become so familiar through popular science that it is easy to forget how strange it actually is. Supermassive, black hole. 3 words that, placed together, describe something for which human language was not really designed, because human language evolved to describe a world of medium-sized objects moving at medium-sized speeds, and Sagittarius A star is emphatically not that. Its mass is approximately 4.15 million times the mass of our Sun. This is a number that resists intuition in the way that very large numbers tend to do. You can read it and nod and feel that you have understood it, and then realize a moment later that you have not understood it at all, because understanding it would require a way of feeling mass that human bodies simply do not have. We experience mass as weight, as the resistance of things when we try to move them. We have no sensory apparatus for 4 million suns. The number sits in the mind like a stone in a pocket, present but not particularly illuminating. So let us try a different approach. You are familiar with Mercury, the smallest planet in our solar system, the one closest to the Sun, the one that completes its orbit in 88 days because it has the shortest path to travel and the strongest gravitational pull urging it along. Mercury moves fast, fast enough that ancient astronomers noticed it zipping across the sky more quickly than anything else, which is why several cultures independently associated it with speed and messengers and things that could not be pinned down. It is our solar system's sprinter, 88 days to circle the Sun. Crisp, efficient, impressively quick by planetary standards. Now imagine that instead of our Sun at the centre of that orbit, there is Sagittarius A star. Same orbital distance, same starting point. Everything identical except that the object doing the pulling has 4.15 million times the gravitational influence. How long would Mercury's orbit take? Not 88 days, not weeks, not even days in the ordinary sense. Mercury, orbiting Sagittarius A star at the same distance it currently orbits our Sun, would complete that journey in approximately 7 hours. 7 hours to travel a path that currently takes nearly 3 months. The planet would be moving at a speed so far beyond anything in our solar system that the comparison stops feeling like a comparison and starts feeling like a different category of thing entirely. Our Mercury, sprinting along its tight little orbit, would look positively leisurely by comparison. It would be lapped. This is what 4.15 million solar masses of gravity actually means, rendered in terms that have some purchase on the imagination. Not a number. A planet moving at a speed that does not belong in the same conversation as anything else in our experience of the solar system. And Mercury is not even close to Sagittarius A star in this thought experiment. The stars that actually orbit near the galactic centre, the ones that have been tracked by astronomers over decades of careful observation, are doing something still more extreme. There is a group of stars known as the S stars, a cluster of massive, young, improbably fast objects in tight orbits around the central point. They should not be there by rights. Stars of that type, hot, young O and B class stars, form from large clouds of gas that require relatively peaceful conditions to collapse. The environment immediately surrounding a supermassive black hole is not, in any sense of the word, peaceful. How these stars came to be where they are is a question that astronomers have not fully resolved, and they are the kind of astronomers who are uncomfortable with fully unresolved questions, so this one is referred to, with characteristic understatement, as the paradox of youth. The most studied of the S-stars is called S2, and S2's orbit is one of the most remarkable things in the observable galaxy. It completes a full orbit around Sagittarius A star in approximately 16 years. 16 years. A human child born at the beginning of one of S2's orbits would be entering secondary school by the time it came back around. And, at its closest approach to the central black hole, a point called periapsis, which sounds like a medication but is in fact an orbital term. S2 reaches a speed of roughly 7,650 kilometers per second. That is approximately 2.5% of the speed of light. Sufficiently fast that the effects of Einstein's general relativity become not merely theoretical, but directly measurable in the star's observed path. S2 is moving fast enough that space-time itself has to be accounted for in the calculations. Imagine watching that from the surface of a nearby planet, a planet that, for the purposes of this imagining, you are somehow surviving on, despite everything we have established about the neighbourhood. You look up at the sky, and where we might see the sun drift slowly through the seasons, you see a massive star completing its entire orbit in the span of a human adolescence, You see it swing close, accelerate to a fraction of light speed, whip around something invisible and enormously heavy and race away again. And then you wait for 16 years, and it comes back. At the centre of all this motion, the invisible anchor around which S2 and its companions endlessly race, sits Sagittarius A star itself. And here is the thing about Sagittarius A star that makes it unusual, even among supermassive black holes. Right now, at this particular moment in the long history of the galaxy, it is quiet, not silent. The surrounding environment ensures that there is always something falling in, some cloud of gas being stretched and heated and consumed, but quiet by the standards of what it could be doing, what other black holes of its kind have been observed doing, what it has almost certainly done before, in the deep past, and may do again. Astronomers describe Sagittarius A star as being in a low luminosity state. This is a polite way of saying that it is not currently feeding with any great enthusiasm. A supermassive black hole that is actively consuming large quantities of surrounding material becomes one of the most luminous objects in the universe. An active galactic nucleus, blazing with the energy of the infalling matter as it spirals inward and heats to temperatures that make stellar surfaces seem cool. Sagittarius A star is not doing that. It is doing something more like the cosmic equivalent of sleeping, patient and enormous, and surrounded by everything it needs to become something far more energetic. Should it choose to wake? It has not chosen to wake. Not today. And we are, in ways we will explore as the night continues, quietly grateful for that. Imagine for a moment that you could feel radiation the way you feel warmth from a fire. Not the dramatic science fiction version of radiation, no glowing, no immediate transformation into something cinematic, just a sensation. A pressure, perhaps, or a heat that comes from no particular direction, the way the warmth of a summer afternoon seems to arrive from the whole sky at once, rather than from any single point. Now imagine that sensation coming not from one direction, but from all of them simultaneously, from above and below and to every side, from the stars packed so densely around you that the sky has no gaps, from the remnants of supernovae drifting through the interstellar medium like the still warm embers of fires that burned out thousands of years ago, from the X-ray sources clustered near the galactic center, from the ultraviolet pouring off massive young stars, from the gamma-ray bursts that punctuate the deeper history of this neighborhood, with a regularity that, from a safe distance, sounds almost routine. This is the radiation environment of the galactic center. Not a beam, not a burst, a field. Something you would be inside rather than adjacent to, surrounding you on every side with the accumulated energetic output of one of the most active regions in the galaxy. It is, in the most literal sense, inescapable. Not because it moves too fast to outrun, though it does, but because there is no direction in which it is not already waiting for you. Radiation, in the ordinary sense of the word, describes the emission of energy as waves or particles. It is a broad category that encompasses an enormous range of phenomena, from the infrared warmth your body gives off to the gamma rays produced in the hearts of dying stars. What these things share is that they travel outward from their source and carry energy with them, depositing that energy into whatever they happen to encounter. Whether that encounter is harmful depends on the type of radiation, the intensity, and the duration of exposure. A brief walk in sunlight is an encounter with radiation that your body handles without difficulty. A brief walk near the galactic center would be an encounter with radiation that your body would not handle at all, and the word brief would take on a meaning that your descendants might find instructive. The galactic center produces radiation across virtually the entire electromagnetic spectrum, and it does so from multiple overlapping sources rather than a single dominant one. This is part of what makes the environment so thorough in its hostility. There is no gap in the coverage, no frequency at which the environment is simply quiet. Young, massive stars, the kind that form in clusters near the galactic center and burn through their fuel in millions of years rather than billions, flood the surrounding gas with ultraviolet radiation intense enough to ionize hydrogen across vast distances, stripping electrons from atoms and leaving the interstellar medium in a perpetual state of agitation. The remnants of supernovae, the expanding shells of gas ejected when those same massive stars eventually exhaust themselves and collapse, heat the medium around them to temperatures of millions of degrees and pour X-rays into the surrounding space for thousands of years after the initial explosion. And from the direction of Sagittarius A star itself, even in its current quiet state, there is a steady trickle of X-ray emission produced by the gas and dust that continues to fall, slowly and incrementally, toward the central point. From Earth, none of this is visible. All of it is hidden. This is one of the stranger aspects of the galactic center as an object of study. A region of such extraordinary energetic activity that it would be lethal to any biology foolish enough to wander into it is, from our perspective, entirely concealed behind 26,000 light-years of intervening dust and gas. The visible light that the galactic center produces, and it produces a great deal of it, is absorbed by the material between us, and it so thoroughly that our eyes receive nothing. The galactic center is invisible. The most dangerous address in the Milky Way hides behind a curtain of dust so thick that you could point a perfectly good optical telescope directly at it and see, essentially, a rather unexciting patch of the Milky Way. This is, depending on your perspective, either deeply frustrating or quietly reassuring. It was through radio and infrared astronomy, wavelengths that can penetrate the dust where visible light cannot, that astronomers began to map the galactic center in earnest, and what those maps revealed was a neighborhood considerably more eventful than the view from Earth suggests. Among the things those maps found, sitting relatively close to Sagittarius A star on the scale of galactic distances, was something that belongs in a category of its own. The object is called SGR 1806-20, and it is a magnetar. A magnetar is a type of neutron star, and you will recall from earlier in our journey that neutron stars are already among the most extreme objects the universe produces, with gravitational fields strong enough to compress a marshmallow to a width smaller than an atom in the first millisecond of contact. A magnetar takes this already considerable extremity and adds to it a magnetic field of such staggering intensity that the neutron star underneath almost becomes the secondary point of interest. Almost. The magnetic field of the Earth is strong enough to deflect the charged particles of the solar wind, and usefully to make compass needles point north, which has been of considerable assistance to navigators throughout history. The magnetic field of a typical neutron star is roughly 1 trillion times stronger than Earth's, a number large enough to be meaningless without an analogy, but strong enough that at a distance of a few hundred kilometers it would rearrange the iron atoms in your body in ways you would find very inconvenient. The magnetic field of a magnetar is stronger still, approximately 1,000 times stronger than a typical neutron star, a quadrillion times stronger than Earth's. At this intensity, The magnetic field is strong enough to distort the very shape of individual atoms, compressing their electron clouds from spheres into elongated filaments aligned with a field direction. Matter, at these field strengths, does not behave the way matter normally behaves. The rules change. Quietly and entirely, and without any interest in whether this is convenient. SGR 1806-20 made itself known to astronomers in a particularly emphatic way on the 27th of December, 2004, when it produced what is called a giant flare, a sudden, violent release of energy caused by a starquake on its surface, the magnetar equivalent of tectonic activity, except that the crust of a magnetar is composed of crystallized neutrons rather than rock, and the energies involved are correspondingly different. The flare lasted approximately a tenth of a second. In that tenth of a second, SGR 1806-20 released more energy than our Sun will emit in the next 100,000 years. Let that settle for a moment. A tenth of a second, 100,000 years of solar output. These two things, placed in the same sentence, resist each other the way oil resists water. The mind wants to separate them into different categories of experience. One is an instant, the other is geological time. And yet the physics insists they belong together. The flare was detected by satellites in orbit around Earth, and it was sufficiently energetic that it partially ionized the upper atmosphere at a distance of 50,000 light-years. From 50,000 light-years away, a tenth of a second of energy output was enough to affect our planet's atmosphere. SGR 1806-20 is approximately 50,000 light-years from Earth. This was, astronomers noted, with the careful restraint of people who have learned not to catastrophize at press conferences, a significant event. What this means for the environment of the galactic center, in whose general neighborhood SGR 1806-20 resides, is that the radiation field we have been describing is not merely the accumulated background output of many ordinary sources. It is punctuated, occasionally and unpredictably. One of the objects in this already extreme environment produces an energetic event that, by itself, would be among the most powerful phenomena in the observable galaxy. The magnetar does not do this on a schedule. It does not send advance notice. It simply, from time to time, releases the energy of 100,000 years of solar output in the time it takes to blink, and the surrounding space adjusts accordingly. The word that comes to mind surveying all of this is saturated. The galactic center is not dangerous in the way that a specific hazard is dangerous. A cliff edge, a deep current, a single identifiable source of harm that can, in principle, be avoided. It is dangerous the way weather is dangerous when you are already inside it. The radiation is not coming from one direction. It is not arriving at one energy level. It has not originated from one source. It is the aggregate output of an entire region of space, where the conditions for producing energetic radiation are maximally favorable, where the density of stars and compact objects and exploding things is higher than almost anywhere else in the galaxy, and where even the relatively quiet central black hole contributes its own steady baseline to the total. And we have not yet discussed what gravity does to matter that gets too close. That is a different kind of danger entirely, and it operates on a different set of principles. But it is waiting, as all things in this neighborhood wait, patiently and without any particular concern for whether we are ready. Gravity, at the distances we experience it in daily life, is a remarkably polite force. It holds you to the ground with a consistency that is easy to take for granted. It keeps the moon in its orbit, and the atmosphere from drifting away and the oceans from rising off the surface and departing for somewhere more interesting. The difference in gravitational pull between your head and your feet, your head being very slightly further from the centre of the Earth and therefore subject to very slightly less gravitational attraction, is so small as to be entirely imperceptible. Your body does not notice it. Your blood does not redistribute itself in response to it. The atoms that make up your left hand are not being pulled any more strongly toward the Earth than the atoms that make up your right. Gravity, at human scales, is smooth, uniform, politely indifferent to the difference between one part of you and another. This ceases to be the case as you approach a sufficiently massive object. And near Sagittarius A star, it ceases to be the case in ways that require an entirely new vocabulary to describe. The force in question is called a tidal force, and it arises from a simple principle. Gravity weakens with distance. Not dramatically, at the distances we normally experience, but measurably, and in the presence of a sufficiently concentrated mass, measurably becomes dramatically very quickly. Imagine, for a moment, that you are falling feet first towards Sagittarius A star. Your feet are closer to the central mass than your head. This means your feet are experiencing a stronger gravitational pull than your head. The difference between the force on your feet and the force on your head is the tidal force, and what it does, with elegant and absolute thoroughness, is stretch you. Not compress, stretch. Along the direction of the gravitational gradient, the difference in force pulls the near end toward the mass more strongly than the far end, elongating whatever unfortunate object happens to be in the way into something that, if the gradient is steep enough, begins to resemble a very long, very thin strand of itself. Physicists call this process spaghettification, which is one of the more descriptive terms in the technical vocabulary of astrophysics, and which has the considerable virtue of conveying exactly what it means without requiring any additional explanation. You would be spaghettified, stretched from a person into something pasta-shaped, which is not, by any measure, an improvement. The rate at which this happens depends on the steepness of the gravitational gradient, how quickly the force changes over the distance of the object in question. And here is something counterintuitive about black holes that is worth taking a moment with. For supermassive black holes like Sagittarius A star, the tidal forces at the event horizon are actually gentler than for smaller black holes. This seems backwards. Sagittarius A star has millions of times the mass of a stellar black hole. Surely it should be more dangerous at the boundary, not less. The reason it is not comes down to size. The event horizon of a black hole, the boundary beyond which nothing can escape, grows in proportion to the mass of the black hole. A more massive black hole has a larger event horizon, and a larger event horizon means that the gravitational gradient across the width of a human body at that boundary is smaller, because the boundary itself is further from the centre. For Sagittarius A star, the event horizon is so large, roughly 24 million kilometres across, which is about 17 times the diameter of our Sun, that the tidal forces at its edge, while certainly not comfortable, would not immediately spaghettify you. You might, in principle, cross the event horizon of Sagittarius A star without feeling an extraordinary tidal force in that precise moment. What you would feel crossing that boundary is something considerably stranger. The event horizon is not a surface. There's nothing there to touch, no wall to encounter, no membrane that your hand would pass through with any particular sensation. It is a threshold defined entirely by geometry, the point in space where the curvature of space-time becomes so extreme that all possible paths forward lead inward, not some paths, all of them. Light itself, which travels in straight lines through flat space, finds that in the curved space-time near a black hole, its straight lines bend increasingly toward the center, until at the event horizon, even a beam of light directed directly outward finds itself moving. From any external perspective, not at all. It is not that the light slows down. Light does not slow down. It is that the space it is moving through is itself falling inward faster than the light can travel through it. This is worth sitting with for a moment, because it is one of the stranger things that general relativity asks us to accept. The event horizon is a place where the fabric of space-time is moving, not where matter is moving through stationary space, but where space itself is flowing, the way a river flows, and where the current has become fast enough that nothing, not even light, which moves at the maximum speed the universe permits, can swim against it. From inside the event horizon, the direction towards Sagittarius A star is not a direction in space. It is a direction in time. Moving toward the singularity is as unavoidable and as one-directional as moving from Tuesday into Wednesday. You cannot choose not to fall further in, any more than you can choose not to move into the future. The geometry of space-time has arranged itself such that inward is the only direction that exists. From Earth, all of this plays out behind a curtain we cannot lift. Sagittarius A star sits 26,000 light-years away, its event horizon invisible not merely because of distance and dust, but because, by definition, nothing from inside it reaches us. The boundary itself is theoretical, real, in the sense that the mathematics is consistent and the physical consequences are measurable in the orbits of nearby stars, but imperceptible from our position in the quiet outer reaches of the galaxy. We can calculate where the event horizon is. We can describe what happens at it. We cannot see it in the ordinary sense of the word, because there is nothing coming from it to see. What we can detect with sufficiently sensitive instruments is the region just outside the event horizon, the area where infalling matter, compressed and heated to temperatures of billions of degrees as it spirals inward, glows with an intensity that escapes before crossing the threshold. This glowing region, the innermost edge of the accretion flow, is the closest thing to a visible signature that a black hole produces. It was this region that the Event Horizon Telescope captured in its 2019 image of M87 star, and in its 2022 image of Sagittarius A star itself, a bright ring of superheated gas, blurred by the extreme gravitational lensing of the black hole behind it, with a dark central shadow that marks the point at which light no longer escapes. The shadow of an event horizon. The closest thing to a photograph of nothing that science has ever produced. And then there is the question of what happens over very long timescales to the black hole itself. In 1974, Stephen Hawking demonstrated mathematically that black holes are not, in fact, perfectly black. They radiate. Slowly, and at a temperature so low that detecting it directly is currently beyond any instrument we possess, but they radiate nonetheless. The process arises from quantum mechanics, from the behavior of virtual particle pairs that form spontaneously at the event horizon, one falling in, one escaping, with the energy for this process drawn ultimately from the mass of the black hole itself. The rate of this radiation is inversely proportional to the mass of the black hole. Sagittarius A star, with its 4.15 million solar masses, radiates Hawking radiation at a temperature of approximately 15 nanokelvin, 15 billionths of a degree above absolute zero, This is not a temperature that any instrument currently in existence could distinguish from absolute zero. It is, for all practical purposes, undetectable, and at this rate, Sagittarius A star would take something in the order of 10 to the power of 87 years to evaporate completely. To offer a sense of scale, the current age of the universe is approximately 10 to the power of 10 years. The black hole will outlast the universe as we know it by a margin that makes the universe as we know it look like a rounding error. But it will not last forever. This is the unexpected grace note in an otherwise unrelenting chapter. Even the most patient, most massive, most comprehensive object in the neighbourhood is temporary. It is burning, imperceptibly slowly on a timescale so vast it dissolves all ordinary intuition. But it is burning. The sleeping giant at the centre of the Milky Way will eventually exhaust itself into nothing, a last faint whisper of hawking radiation in a universe so old that the stars themselves will have long since gone dark. That is a long way from now. For the moment, it simply sits there, patient and enormous, while the radiation saturates the space around it and the stars race past in their improbably tight orbits, and the rest of the galaxy goes quietly about its business, mostly unaware of what it is orbiting. We have been describing Sagittarius A star at its quietest, patient, subdued, consuming just enough to remind the surrounding neighbourhood of its presence, but not enough to do anything that would draw attention from further afield. A sleeping giant, as we said at the beginning, surrounded by everything it needs to become something far more energetic, should it choose to rouse itself. It is worth spending some time with what that actually means, not as an abstraction, but as a concrete change to the world you inhabit, because the difference between a dormant, supermassive black hole and an active one is not a difference of degree in the way that the difference between a warm day and a hot day is a difference of degree. It is a difference in kind, a transformation so total that the galaxy containing it becomes, in the most literal sense, a different place to live. Imagine that you are standing outside on a clear night, not in a city but somewhere genuinely dark, a field perhaps or a hilltop, the kind of place where the Milky Way is properly visible as a band of light, rather than an architectural detail you occasionally remember exists. The sky above you is doing what it has always done, holding its stars at their comfortable distances, the brightest ones crisp and steady, the fainter ones dissolving at the edges of perception. The moon, if it is present, outshines everything. If it is not, the night is simply dark, in the way that nights have been dark for as long as there have been nights. You can see, but you are also unambiguously in the dark. Now imagine that Sagittarius A star wakes up. Not instantaneously. These things take time, measured in thousands of years rather than moments. But imagine that, over the long, slow, geological span of its awakening, Sagittarius A star begins to feed in earnest. A gas cloud drifts too close and begins to spiral inward, then another. The accretion disk, which currently exists only in a thin, dim, tentative form, begins to build. Matter piles up. Friction generates heat. The innermost regions of the disk climb to temperatures of millions, then hundreds of millions of degrees. And the energy released by this infalling matter, which is, by the physics of gravitational accretion, a significant fraction of the matter's total mass energy, a conversion efficiency that nuclear fusion cannot approach, begins to radiate outward across every wavelength simultaneously. From 26,000 light-years away, you would notice. The galactic centre, which is currently invisible to the naked eye, would become visible. Not faintly, not as a new star among the existing stars, but as a new source of light, with no precedent in the sky you have always known. It would appear in the direction of Sagittarius, somewhere near the heart of the Milky Way's central bulge, and it would brighten as the accretion disk developed, climbing in intensity over millennia until it reached a luminosity that the night sky has not hosted since the universe was young. At its peak, a fully active Sagittarius A star, a true active galactic nucleus, would be visible in full daylight. It would cast shadows at night, not the soft, directionless luminance of a full moon, which scatters across the sky and arrives from above, but sharp-edged shadows from a single, concentrated source, sitting low in the southern sky, fixed and blazing, present every night of the year. Think about what that sky would look like. A second source of light in the darkness, not as bright as the sun, but far brighter than anything the night has ever contained. Bright enough that you could read by it. Bright enough that the hemisphere facing it would never fully darken. Bright enough that the stars in its vicinity would be washed out by the glow around it, a halo of ionized gas and gravitationally lensed light spreading across several degrees of sky. The Milky Way, which currently appears as a pale, diffuse band, would be transformed, its centre ablaze, its surrounding clouds of gas lit from within, the whole structure of the inner galaxy made suddenly starkly visible in a way it has not been for billions of years. And that is the relatively modest end of what an active galactic nucleus can do. Elsewhere in the universe, at greater distances in earlier epochs, in galaxies whose central black holes had more material to consume and consumed it with more enthusiasm, the phenomenon reaches scales that make a merely active Sagittarius A star look restrained. These are quasars, and they are among the most luminous objects the universe has ever produced. A quasar is simply an active galactic nucleus viewed from a sufficient distance that the host galaxy around it fades to imperceptibility, and what remains in the telescope image is a point of light so bright it was initially mistaken for a star. The name is a contraction of quasi-stellar object, which was the careful, appropriately hedged terminology of astronomers who knew they were looking at something unusual but had not yet worked out what. What they were looking at, it eventually emerged, was a galaxy's worth of material being consumed by a black hole at a rate that converted the infalling mass into radiation with a profligacy that makes even the most active stellar processes look frugal. The most luminous quasars outshine the entire galaxy surrounding them by factors of hundreds or thousands. They are brighter than 1 trillion suns. Not 1 trillion suns arranged across a galaxy in the usual way, distributed and diluted by the distances between them, but 1 trillion suns worth of energy emerging from a region not much larger than our solar system. Concentrated, focused, impossible to look at directly, if you could somehow be close enough to look, which you could not, because the radiation environment in the vicinity of a luminous quasar would be fatal at distances that would take light thousands of years to cross. Some quasars go further still, when the jet of plasma and energy that a feeding black hole can produce, a column of superheated material launched perpendicular to the accretion disk at close to the speed of light, extending for thousands or even millions of light years, happens to point directly toward Earth. What we observe is called a blazar. The jet is not simply bright, it is Doppler boosted, its apparent luminosity amplified by its relativistic motion toward us, and it is variable, flickering and flaring on timescales of hours as the internal structure of the jet shifts and adjusts. Blazars are among the most energetic sustained phenomena in the observable universe. They are also, from the perspective of any hypothetical biology in their path, the universe's least subtle way of communicating that a particular direction is best avoided. All of this is for the moment happening elsewhere, in other galaxies, at other distances. Sagittarius A star is quiet, and the Milky Way is, in the cosmic register, a calm and middle-aged galaxy that has not hosted a major active nucleus for a very long time. There is evidence in the structure of certain gas clouds near the galactic center, in the traces of high-energy radiation that appear to have swept through the inner galaxy in the geologically recent past, that Sagittarius A star was more active some millions of years ago, producing outflows energetic enough to leave marks on the surrounding medium that we can still detect today, but millions of years ago, in the long timescale of a galaxy, is ancient history. By the time anything with eyes arrived on the third planet of a quiet star 26,000 light-years away, the active phase was long over. We exist, in other words, in the quiet aftermath of something considerably more dramatic. And the fact that we exist at all, that the Earth has an atmosphere, that the atmosphere has not been stripped away by radiation, that the chemistry of life had billions of years of relative calm, in which to develop from simple molecules into something capable of lying in the dark and wondering about all of this, is not entirely unrelated to the fact that Sagittarius A star ran out of easily available food before we arrived. The timing, from our perspective, was fortunate. The universe, as usual, was simply indifferent. There's a version of the Milky Way in which none of this was true, in which the gas clouds that drifted too close to the center in the right sequence, at the right time, sustained an active nucleus for long enough to reshape the inner galaxy entirely, in which the night sky for any creature that had managed to evolve on any planet within range would have contained that second terrible sun, blazing and shadow-casting and utterly permanent, in which the conditions for the quiet, slow, patient chemistry of life would have been considerably harder to sustain. That version of the Milky Way is not impossible. It is simply not the one we are in. And on balance, staring up at a dark sky in which the galactic center is invisible, the distinction seems worth appreciating. It would be unfair, having spent this much time in the galactic center, not to acknowledge the competition. The universe is large, and it is not lacking in ambition when it comes to producing environments that are hostile to organized matter. The galactic center has made a strong case for itself. The radiation field, the magnetars, the tidal forces, the sleeping supermassive black hole, and the considerably less sleeping version we visited in its active state. But there are other candidates, and they deserve a fair hearing before we arrive at any conclusions. Science, at its best, considers all the evidence before rendering a verdict, and the evidence in this case includes some objects that are genuinely extraordinary in their own right, even if they ultimately fall short on the specific grounds we are using to judge. Let us return briefly to neutron stars. We encountered them earlier as an illustration of how the lethal radius of an object expands as we move up the scale of cosmic extremity, and we noted that they are already among the most compressed objects the universe produces, with surface gravities strong enough to compress ordinary matter into forms it was never designed to take. But we did not linger on them as long as they perhaps deserved, and they merit a more considered look. A neutron star is born in the aftermath of a supernova, the explosive death of a massive star whose core, having exhausted its nuclear fuel, collapses under its own gravity in a fraction of a second. If the collapsing core has enough mass, it passes through the neutron star phase and continues into a black hole. But if it lands in a particular range of masses, roughly between 1 and 3 times the mass of our Sun, it stops at neutron star densities. and neutron star densities are, by any reasonable measure, extraordinary. Imagine taking the entire mass of the Sun, 2 octillion tons, a number so large it has essentially no meaning outside of the mathematical context that produced it, and compressing it into a sphere roughly 20 kilometres across. The city of Brisbane, the city of Zurich. A sphere you could theoretically drive around the equator of in about an hour, if the road surface were not composed of crystallized neutrons at a density of approximately 400 million tons per cubic centimetre, which would present certain engineering challenges. The resulting object has a surface gravity approximately 200 billion times stronger than Earth's, a magnetic field that dwarfs anything else in the ordinary stellar catalogue, and a surface temperature in the aftermath of formation of around 1 million degrees. Neutron stars also rotate. This is not surprising. All stars rotate, and when a rotating star collapses, conservation of angular momentum causes the resulting neutron star to spin considerably faster than its progenitor. What is perhaps surprising is how fast. The fastest spinning neutron stars, a class called millisecond pulsars, rotate hundreds of times per second, not dozens, hundreds. There is a pulsar catalogued with the arrestingly unromantic designation PSRJ 1748-2446AD that completes 716 full rotations every second. Its equatorial surface is moving at approximately a quarter of the speed of light. This is a solid object, spinning so fast that the physics of what holds it together begins to brush against the limits of what our understanding of matter can comfortably accommodate. It does this continuously, without apparent effort, and has been doing so for longer than human civilization has existed. As it spins, it sweeps twin beams of radiation from its magnetic poles across the surrounding space, the way a lighthouse sweeps its beam across water, except that the lighthouse in question is 20 kilometres across, rotating 700 times per second, and the beam is composed of radio waves and X-rays rather than visible light. If one of those beams happens to intersect the Earth with each rotation, we detect the pulsar as a series of extraordinarily regular pulses, so regular, in fact, that when Jocelyn Bell Burnell first detected the signal in 1967, the initial, briefly entertained explanation was that it might be artificial. The regularity was simply too precise to seem natural. It was not artificial. It was a neutron star doing what neutron stars do, with the mechanical consistency of an object that has no particular interest in whether it is being observed, and every physical reason to keep spinning. Magnetars, as we have already established, take the neutron star template and amplify its most extreme feature to a degree that places them in their own category. The magnetic field of a magnetar is not merely stronger than a typical neutron star's. It is strong enough to alter the fundamental behavior of the vacuum itself, to affect the way light propagates through empty space in the magnetar's vicinity, a phenomenon called vacuum birefringence that sits at the boundary between classical electrodynamics and quantum field theory and makes physicists write excited papers. The environment immediately surrounding a magnetar is genuinely unlike any other environment the universe produces. The rules that govern the behavior of matter and energy in ordinary conditions apply only approximately, and in some cases, not at all. So why, with all of this on offer, does the galactic centre still hold the title? The answer comes down to a distinction that sounds simple but turns out on examination to carry a great deal of weight. A neutron star, a pulsar, a magnetar. These are points, extraordinarily dangerous points surrounded by extraordinarily dangerous fields, but points. Their influence is local. Stand far enough away from even the most energetic magnetar, and you are safe. Not comfortable, perhaps, and not entirely free of its influence, but safe in the sense that the forces it exerts have diminished to levels that matter can survive. The inverse square law is generous to those with sufficient distance, and the universe, outside the immediate vicinity of these objects, is largely indifferent to their existence. The galactic centre does not offer this comfort. It is not a point, it is a region, a volume of space hundreds of light-years across, in which the density of extreme objects, the intensity of radiation from overlapping sources, and the gravitational influence of a 4 million solar mass black hole combine into something that has no clear boundary where it simply stops. You cannot move to the far side of the galactic centre's radiation field the way you can move to the far side of a magnetar. The field has no far side that is safe in any straightforward sense. The hazard is ambient. It is the background condition of the territory, not a feature attached to a single location. This is the distinction that matters when we talk about the most dangerous place in the universe. Not the most instantly lethal, not the most powerful at a single point, but the most comprehensively, persistently, and inescapably hostile across the largest sustained volume of space. A gamma-ray burst, which we might reasonably nominate as the most acutely lethal event the universe produces, lasts seconds to minutes and affects a narrow beam of space. A magnetar flare releases more energy than the sun will emit in 100,000 years in 1/10 of a second, but from across the galaxy it is a pulse, a brief spike in the data, and then it is over. These things are catastrophic in the way that a lightning strike is catastrophic, sudden, overwhelming, and localized in both space and time. The galactic center is not a lightning strike, it is the weather. And the weather, in this neighborhood, has been running continuously for longer than the Earth has existed, and shows no particular signs of improving. For a human body, it should be said, the distinction is largely academic. Whether you are destroyed by the most acutely lethal event in the universe, or by the most persistently hostile environment in the universe, the outcome is the same, and it arrives before you have had time to form an opinion about which category of danger you prefer. The competition between these candidates is not really a competition that matters to anything biological. It is a competition of descriptions, of categories, of the way we choose to sort and define the extremes that physics produces. And the category we have chosen, sustained, ambient, large-scale, structurally hostile, points clearly to one address. We will arrive there shortly. But before we render a final verdict, there is one more thing worth considering. Not the dangers of the galactic centre, but the extraordinary fact that we know about them at all. That from a quiet planet orbiting a quiet star in a quiet corner of a middle-aged galaxy, we have managed to map a region we cannot visit, image an object we cannot see, and describe an environment that would end us in the time it takes to form the first syllable of a response. How we came to know what we know is, in its own way, as remarkable as what we know. Consider, for a moment, what we have actually been doing for the past several hours. We have been describing, in some detail, an environment that no human has visited, that no instrument has been physically present in, that is hidden from our eyes by 26,000 light-years of intervening dust and gas, and that would destroy any probe we could conceivably send toward it long before it arrived. We have described the temperature of infalling matter, the orbital speeds of individual stars, the intensity of radiation fields, the magnetic properties of objects 20 kilometers across, and the shadow cast by an event horizon across a ring of superheated gas. We have done all of this with a confidence that, if you stop to examine it, is either entirely justified or extremely audacious. It is, as it happens, entirely justified. But the story of how it became justified is worth telling, because it is one of the more quietly remarkable things that human curiosity has managed to pull off. The galactic centre, as we have established, is invisible. Point an ordinary optical telescope at the heart of the Milky Way, and you will see nothing of consequence. The dust and gas between here and there absorb visible light so thoroughly that the most powerful optical instrument ever built would fare no better than your naked eye in that particular direction. For much of human history, the centre of the galaxy was not merely unknown, but unknowable, hidden behind a curtain that no available technology could penetrate. Astronomers knew the Milky Way had a centre, in the same way that you know a city has a centre, even if you have never been there. But knowing something exists and being able to study it are different things entirely. The breakthrough came in the middle of the 20th century, when radio astronomy transformed what could be observed. Radio waves, unlike visible light, passed through interstellar dust without significant absorption. They travel across the galaxy's intervening material the way a long-wave radio signal passes through walls, not deflected, not absorbed, simply continuing on their way with a sublime indifference to the obstacles between transmitter and receiver. When astronomers turned radio telescopes toward the galactic centre for the first time, the curtain, from the radio perspective, was not there. What they found behind it was a compact, powerful radio source, sitting precisely where the gravitational dynamics of the surrounding stars suggested the galactic centre should be. It was detected in 1974 by Bruce Ballack and Robert Brown, and it was given the designation Sagittarius A star using the notation system for compact radio sources, and the name has stuck, which tells you something about how astronomers feel about rebranding things that already have perfectly serviceable designations. Infrared astronomy opened another window. Infrared radiation, like radio waves, penetrates the interstellar dust that blocks visible light, and infrared telescopes, which must be cooled to extremely low temperatures to prevent their own heat from overwhelming the faint signals they are trying to detect, a technical challenge that makes building them somewhat more complicated than it sounds, revealed the galactic centre in new detail, the dense star clusters, the gas clouds, the hot, young, improbably located stars whose existence in the vicinity of a supermassive black hole continues to present astronomers with questions they have not fully answered. Infrared imaging turned the galactic centre from a radio source into a place, a region with structure and population, and a visible character that could be mapped and catalogued and argued about at conferences. But it was the patient, decades-long work of tracking individual stars that produced the most direct and compelling evidence for what sits at the centre of all of it. Imagine standing in a field at night and watching the grass move. You cannot see the wind, but you can infer the wind, its speed, its direction, its gusts and lulls, from the way the grass responds to it. The grass is your instrument. Its motion is your data. And given enough time and careful observation, you can build up a precise picture of something entirely invisible. This is, in essence, what two independent teams of astronomers, one led by Reinhard Genzel at the Max Planck Institute in Germany, the other by Andrea Ghez at UCLA, spent the better part of 3 decades doing with the S-stars. Using increasingly sophisticated infrared telescopes and adaptive optic systems that correct in real time for the blurring effect of Earth's atmosphere, they track the positions of individual stars near the galactic centre, year after year, accumulating data points that, assembled together, revealed orbital paths. And from those orbital paths, by applying the same mathematics that Kepler used to describe the motion of planets around the Sun, They derived the mass of whatever was pulling those stars into their improbably tight, improbably fast trajectories. The number that emerged was unambiguous: 4 million solar masses, concentrated into a region so small that no known collection of ordinary objects, no cluster of neutron stars, no dense assembly of stellar remnants could fit within it without collapsing into something considerably more compact. The only object consistent with the observations was a supermassive black hole. The evidence was, by any reasonable scientific standard, conclusive. Reinhard Genzel and Andrea Ghez shared the Nobel Prize in Physics in 2020 for this work, which was the physics community's way of saying that watching stars orbit an invisible point for 30 years and correctly deducing what the invisible point must be is exactly the kind of thing that deserves a Nobel Prize. All of this, however, remained indirect. The black hole was inferred from the behaviour of the things around it, the way a planet is inferred from the wobble it induces in its host star. What astronomers had not yet managed was a direct image of the object itself, or rather, of the region immediately surrounding it, since by definition the black hole itself produces no image. That changed in April 2019, and again in May 2022. The Event Horizon Telescope is not a single telescope. It is an array of radio telescopes distributed across the surface of the Earth, in Hawaii, in Chile, in Spain, in Arizona, in the South Pole, that are coordinated to observe simultaneously and whose data is combined using a technique called very long baseline interferometry. The effective aperture of this arrangement is approximately the diameter of the Earth itself. This is the largest telescope that can be built without leaving the planet, and it was built specifically to resolve structures at angular scales small enough to image the shadow of a black hole's event horizon at galactic distances. The data collected during each observation run fills hard drives that are then physically shipped to processing centers, because the volume of information involved exceeds what can be transmitted over the internet in any practical time frame. Radio astronomy at the frontier turns out to involve a surprising amount of logistics. In 2019, the Event Horizon Telescope released its first image, the supermassive black hole M87 star at the centre of the galaxy Messier 87, 55 million light-years away. A bright, asymmetric ring of orange-gold light surrounding a dark central shadow. The ring is the innermost accretion flow, the matter spiralling inward just before it crosses the threshold. The shadow is the photon sphere and event horizon, the region from which no light escapes. It was the first direct visual evidence of a black hole's existence, and it looked almost exactly as the mathematics had predicted it would, which is the kind of outcome that makes theoretical physicists feel that the decades they spent on the calculations were well spent. In May 2022, the same collaboration released an image of Sagittarius A star. The same structure, a glowing ring, a dark shadow, but smaller, closer, and considerably more difficult to produce. Sagittarius A star is much lighter than M87 star, and the material around it orbits and varies on timescales of minutes rather than days, meaning that the source was changing faster than the data could be collected in a single snapshot. The team effectively had to average across hundreds of images taken over multiple observation nights, disentangling the variability from the underlying structure to produce the final result. What emerged was a blurred, glowing ring of radio emission, the shadow at its centre slightly less crisp than M87 stars, but unmistakable. It was a photograph of the object at the centre of our own galaxy, taken from Earth through 26,000 light-years of intervening material, using a telescope the size of a planet, processed by a team of hundreds of scientists over several years, and assembled from hard drives that had been flown in from telescopes on multiple continents. The image itself is not large. It fits comfortably on a phone screen, but it is a direct look at something that for most of human history was not merely unseen but unseeable, and the fact that it exists at all is a testament to a particular quality of human curiosity that has no particular name but is recognizable when you see it. The refusal to accept that the invisible must remain so simply because looking at it is very, very difficult. The universe keeps no secrets from patient curiosity. It simply requires sometimes that the curiosity be exceptionally patient and willing to ship a great many hard drives. Everything we have described so far, the galactic center, the radiation field, the sleeping giant and its active counterparts elsewhere in the universe, exists in the cosmos as it is right now, or rather, as it was when the light left its source, which for objects at astronomical distances is not quite the same thing, but close enough for the purposes of an evening's conversation. We have been, broadly speaking, describing the present. But the universe has a past, a long one, and the past, it turns out, was considerably more energetic than the present in ways that reframe everything we've been saying about what is dangerous and where. Imagine winding the clock back. Not a few thousand years, not a few million, but a few billion. Somewhere between 8 and 12 billion years ago, depending on which part of the sky you are looking at and which galaxies you are using as your reference points. The universe at that time was younger, denser, and in the middle of doing something it has largely finished doing since, building its supermassive black holes. Black holes grow by consuming. In the early universe, galaxies were younger, richer in gas, and had not yet settled into the relatively calm, gas-depleted structures that most of them, including our own Milky Way, are today. There was more raw material available. Gas clouds were larger and more abundant. The rate at which matter fell toward the centers of galaxies was dramatically higher than it is now, and the supermassive black holes at those centers responded accordingly. They fed, enthusiastically and for long, sustained periods, in ways that Sagittarius A star, in its current quiet state, does not remotely resemble. The result was that the early universe was saturated with active galactic nuclei in a way that the present universe simply is not. Where today we observe quasars at great distances, seeing them as they were billions of years ago, because that is when their light began its journey toward us. The early universe contained them not as rare, distant phenomena, but as common features of the galactic landscape. A significant fraction of all galaxies in a certain epoch of cosmic history hosted active nuclei. Not the majority, but enough that wherever you looked in the young universe, the odds of finding a blazing, radiation-saturated galactic center somewhere in your field of view were high. The universe in its youth was lit up from the inside. What this meant for the conditions of life, or rather for the conditions under which life might hypothetically have considered arising, is straightforward enough to state. The ambient radiation levels across the observable universe were dramatically higher than they are now. Not locally, not in a single dangerous neighborhood, but globally. The ultraviolet and X-ray background, the radiation field that fills intergalactic space and filters into every corner of every galaxy, was more intense by orders of magnitude. A planet in that universe attempting to sustain the kind of slow, patient chemistry that eventually produces something capable of asking questions about its environment would have been working against a background that was simply much harder to work against. Not impossible. The chemistry of life is remarkably persistent, and there are arguments that some form of biology might have found ways to proceed even in harsher conditions. but harder, significantly harder. There is also the matter of the galaxies themselves. In the early universe, galaxies were not only more gas-rich but more prone to collision and merger. The large-scale structure of the cosmos, the web of filaments and voids along which galaxies are distributed, was still assembling itself, and galaxies were moving through a denser medium, encountering each other more frequently, disrupting each other's structure, and funneling fresh gas toward their central black holes in the process. Galaxy mergers are one of the most reliable ways to trigger an episode of active galactic nucleus activity. Two galaxies collide, their gas clouds are shocked and compressed, vast quantities of material fall toward the newly combined center, and the black hole at that center, suddenly finding itself with more food than it has had in a long time, obliges. The early universe, which was busy assembling its galaxies through exactly this kind of collision and merger, was therefore busy triggering exactly this kind of activity over and over in galaxy after galaxy across the observable cosmos. It is not, in other words, that the galactic center of an active galaxy is a rare and special configuration that exists only in the most unusual circumstances. It is the configuration that most of the universe's galaxies were in for a substantial portion of cosmic history. What is rare and special from the perspective of deep time is the quietness of the universe we inhabit now. The calm is the exception, the violence was the norm. The peak of quasar activity in the universe, the period of maximum feeding, maximum luminosity, maximum radiation across the cosmos, occurred roughly 10 billion years ago, give or take a billion in either direction depending on the specifics of how you measure it. This is sometimes called the Quasar epoch, and it was a period during which the universe was, from the perspective of any hypothetical biology paying attention, conducting itself in a way that would have been difficult to ignore. The integrated light output of all the active galactic nuclei in the observable universe during that period exceeded the combined light output of all the stars in all the galaxies by a significant factor. The quasars outshone the galaxies, not individually, though many of them did that too, but in aggregate. The universe's brightest sources during its most active period were not the stars. They were the black holes eating the gas around the stars. Since then, things have quietened down. The gas supply has diminished as the black holes consumed it and as star formation converted it into stars, which are considerably less useful as black hole food than raw gas clouds. The merger rate has declined as the large-scale structure of the universe matured and galaxies settled into more stable configurations at greater separations from each other. The active galactic nuclei that blazed so prolifically 10 billion years ago have, one by one, run out of material and subsided into the low luminosity states that characterize most supermassive black holes today. Sagittarius A star, quiet in its current condition, is entirely typical of where most of its kind have ended up, enormous, ancient, and no longer particularly hungry. What we are living in, then, is a particular phase of cosmic history, not the beginning. The universe is nearly 14 billion years old, and we arrived at what amounts to a late hour in its story. Not the end, which is a great deal further away than any time scale that matters for anything biological, but a specific window, late enough that the quasar epoch has passed, and the ambient radiation levels have dropped to something a planet with a decent atmosphere can manage, early enough that the stars still burn and the galaxies still have the gas needed to form new ones. This window is not permanent. It is not guaranteed. It simply happens to be the window in which we find ourselves, and in which the conditions for the kind of slow, patient chemistry we are made of had the room to operate. There is something worth sitting within that, not the vertigo of it, the 14 billion years, the quasar epoch, the long, slow cooling of a universe that was once far more energetic than it is today, but the quieter implication that the relative calm in which we exist, the darkness of the night sky, the invisibility of the galactic centre, the sleeping rather than waking state of Sagittarius A star, none of this is permanent. It is not the universe's resting state. It is a phase, a particular chapter in a much longer story, during which the conditions happen to be hospitable enough for something to look up and start wondering about the rest. The calm we take for granted is not a feature of the universe. It is a phase, and phases by their nature do not last forever. Which brings us, at last, to the question we have been circling since we began. We have seen the galactic centre in its current quiet form. We have seen what it becomes when it wakes. We have measured the competition and found it wanting on the specific grounds that matter. We have traced the history of a universe in which the conditions we are describing were not exceptional but ordinary. And now it is time to assemble the full picture, lay it out plainly, and say clearly what all of this has been pointing toward. We began by establishing what we meant by dangerous, not the most dramatically lethal, not the most instantly fatal, but the most comprehensively, persistently, and inescapably hostile across the largest sustained volume of space. This distinction mattered, because without it the question has no clear answer. A gamma-ray burst is more instantly lethal than anything the galactic centre produces. The interior of a neutron star is denser than anything the galactic centre contains. A magnetar's surface, in the moment of a giant flare, releases energy at a rate that nothing in the galactic centre quite matches at a single point. But none of these is a place in the sense we meant. They are moments or surfaces or objects. They are localized catastrophes in a universe that is otherwise content to simply be very large and very cold. The galactic centre of a galaxy with an active supermassive black hole is a place, a region, a sustained, ambient, structurally hostile volume of space that has been doing what it does not for a second or a century, but for millions upon millions of years, and will continue doing it for millions more. This is the criterion that matters, and by this criterion, the answer has been clear since we first arrived in the neighbourhood. What makes the environment of an active galactic centre uniquely hostile is not any single component, but the convergence of all of them. Begin with the radiation field, which is not a beam or a burst, but a saturating presence across the entire electromagnetic spectrum, produced by overlapping sources. Young massive stars, supernova remnants, accreting compact objects, the central black hole itself, with no gap in the coverage and no direction from which it is not arriving. Add the compact objects embedded in that radiation field, the pulsars sweeping their beams through the surrounding gas, the magnetars sitting in their extraordinary magnetic configurations with their capacity for flares that release more energy in 1/10 of a second than a star emits in 100,000 years. Add the density of the stellar environment itself, so packed that the sky has no dark patches, that solar systems race past one another at speeds that dwarf anything in the outer galaxy, that the rate of stellar birth and death is orders of magnitude higher than in the quiet arms where we reside. And then add, at the centre of all of this, the black hole. 4 million solar masses of compressed gravity in the case of our own galactic centre, and considerably more in the most extreme active galactic nuclei the universe has produced. The gravity that bends the paths of stars into 16-year orbits at thousands of kilometres per second. The accretion disk, when active, converting in falling matter into radiation with an efficiency that nuclear fusion cannot approach, blazing with the combined luminosity of 1 trillion suns from a region no larger than our solar system. The jets of plasma and energy fired at close to the speed of light and extending for millions of light years in both directions, carving through the intergalactic medium and depositing energy across scales that make the host galaxy itself seem small. The tidal forces at the inner boundary, stretching matter into threads along the gravitational gradient with a thoroughness that leaves nothing intact. And beyond the event horizon, the complete and permanent absence of any outward direction, the geometry of space-time rearranged such that inward is the only possibility, time and space exchanging their usual roles, the future defined not by choice but by the mathematics of a mass too large to resist. No single component of this environment, taken in isolation, is unique to the galactic center. Radiation fields exist everywhere. Neutron stars and magnetars are found throughout the galaxy. Gravity is a universal force. What the galactic center does is concentrate all of these simultaneously into a single region and sustain them continuously. The overlapping hazards reinforcing and compounding each other in ways that no individual object can replicate. The danger is not additive, it is convergent, and convergence, in physics as in most things, produces something qualitatively different from the sum of its parts. It is also worth saying clearly one final time what distinguishes this verdict from the obvious alternatives. Gamma-ray bursts are more powerful at a single moment, in a single direction, for a duration of seconds to minutes. They are the universe's sharpest instrument, lethal across enormous distances, but directional and brief. The early universe, during the Quasar epoch, was more uniformly dangerous across larger volumes than any single galactic center today, but it was also a period, not a place, and it has passed. The interior of a black hole, beyond the event horizon, is arguably the most extreme environment physics describes, but it is not a place that anything arrives at without having already been destroyed by everything outside it, and in any case, nothing that crosses the threshold has any subsequent perspective from which to assess conditions. The galactic center wins not by being the most extreme in any single dimension, but by being the most comprehensively hostile across all of them simultaneously, in a region you could, in principle, approach, from which there is no safe distance, and which has been this way for longer than the Earth has existed. Sagittarius A star, our own contribution to this category, is currently the quieter version of what we have been describing. It is dormant rather than active, consuming just enough to maintain its reputation without committing to anything more ambitious. The environment around it is extreme by every standard except that of its own active counterparts elsewhere in the universe. If it were to wake, if the next large gas cloud to drift too close were to trigger a sustained episode of feeding, the Milky Way would become, from the inside, a very different galaxy. It would not happen quickly. Geological time is the appropriate unit, but the potential is there, sitting at the center of everything, patient and enormous, waiting for nothing in particular. There is something in that patience that seems worth noting. The universe is not trying to be dangerous. It has no agenda. The radiation fields, the tidal forces, the accreting black holes, the magnetar flares, none of these are directed at anything. They are simply the consequences of physical laws operating at scales and energies for which those laws were not calibrated by anything with an interest in survival. The universe did not produce these environments in order to make things difficult. It produced them because physics, given sufficient mass and energy and time, cannot help but produce them. They are not hostile. They are indifferent. And indifference at sufficient scale is more thorough than hostility has ever managed to be. From where we are, 26,000 light-years away, on a planet whose magnetic field and atmosphere and orbital distance have conspired to make its surface one of the more comfortable places in the observable universe. None of this is directly perceptible. The galactic center is invisible. Sagittarius A star produces no signal that our eyes can detect. The stars that orbit it at thousands of kilometers per second are too faint and too distant to resolve without the instruments that took decades to build. The most dangerous address in the Milky Way hides behind its curtain of dust, going about its business with the serene indifference of something that has never needed to be found in order to exist. And yet we found it. We mapped it, measured it, imaged it, named the forces operating within it, and described those forces in language precise enough to calculate the orbital period of a star 26,000 light-years away to within a fraction of a percent. We did this from a planet using instruments that required centuries of accumulated mathematics and physics and engineering to produce, operated by people who will live their entire lives at a comfortable remove from the thing they spent those lives understanding. There is a version of this that seems straightforwardly absurd, that creatures who cannot survive unprotected in the ordinary vacuum of space have, through the careful application of curiosity, produced a precise and detailed account of the most hostile environment the universe contains. And yet here we are. The universe keeps no secrets from curious minds, even if it would destroy curious bodies. Somewhere in the direction of Sagittarius, behind more dust and gas than light can cross, 4 million suns worth of gravity curves space-time around a point of absolute darkness. The stars nearest to it are racing. They have always been racing. They will still be racing long after everything we have built has dissolved back into the elements it was made from. They do not know they are remarkable. They are simply doing what the geometry requires, swinging close and pulling away and swinging close again, in orbits that will continue for longer than the Earth has left to offer. And from here, from wherever you are lying right now, in the warmth of an atmosphere that has spent 4 billion years becoming exactly hospitable enough for you to exist inside it, none of it is visible. The galactic center is hidden. The sleeping giant is dark. The most dangerous address in the Milky Way is, from this distance, simply a slightly brighter smudge in a sky full of them, unremarkable to the naked eye, going about its patient and enormous business without any awareness that it has spent this evening being discussed. The universe does not know we are watching. It never has. It simply continues, indifferent and extraordinary, producing its magnetars and its quasars and its racing stars and its curtains of dust on timescales that make a human lifetime look like a rounding error in a very long calculation. And we, small and briefly here, and extraordinarily lucky in our timing, watch. If these quiet journeys through deep space and deep time bring you something, a little stillness, somewhere to let the mind drift while the night grows late, the sleepy astronomer will be here for the next one. For those whose curiosity turns toward the Earth rather than away from it, the slow drift of continents, the deep biography of rivers, the long patience of stone. The sleepy geographer is waiting, and for those drawn to darker, quieter mysteries, the sleepy investigator has something for you as well. The stars are where they have always been. The galactic centre is where it has always been, and somewhere in the dark, patient and enormous, something with the mass of 4 million suns sits quietly at the heart of the galaxy we call home. It is not going anywhere. Neither are you. Sleep well. This is the sleepy astronomer, wishing you clear skies, peaceful dreams, and the quiet comfort of living in a universe young enough to be dark, old enough to be beautiful. Good night, and sleep well beneath the darkness that made you possible.